Hi, I'm Pierre Demier. I'm the director of the New Frontiers of Sound Science and Technology Center, or NewFoS Center. I want to tell you a little bit about the research objective of our center.
Hi, I'm Sara Chavarria, and I'm the director for the NewFoS, New Frontiers of Sound, education and broadening participation programs that we are launching through the center.
Hello, I'm Keith Runge, the Knowledge Transfer Director for the New Frontiers of Sound Science and Technology Center, funded by the National Science Foundation. At NewFoS, the New Frontiers of Sound Science and Technology Center,
We are focusing on the notion of topological acoustics, or in other words, the geometry of acoustic waves or sound, which is a surprising concept, but by manipulating the geometry of acoustic wave and the sound, what we can do is achieve extraordinary properties that can lead to interesting technologies and very important applications in quantum information science, in telecommunication, and in sensing.
We are very excited about all of our projects because they involve student engagement in ways that we feel are unique and innovative. They get to work, for example, on a textbook we're designing and help us vet the content and see how we can improve it so it's more relatable and accessible. We're also very interested in the societal impact elements of the research of this work, which have some implications in all three of the project areas: telecommunications, the quantum-like work that we're doing, and sensing across both environments and human-engineered materials.
we think of knowledge transfer and integration together. Integration is working with the members of the center. We visit each of the universities that are and other institutions involved in the center, working with Araceli Hernandez Granados, who is the research scientist for knowledge transfer.
In terms of quantum information science, we are exploiting the analogy between quantum mechanics and topological acoustic waves. This enables us to design and construct and operate a quantum analog computer based on acoustic waves that avoids the drawbacks of current quantum information technologies. In terms of telecommunications, we are exploiting the extraordinary properties of topological acoustic waves, which may propagate in one direction, but do not reflect when they meet an obstacle. That is, there is no echo for that wave. These waves are going to be very useful in designing surface acoustic wave devices, micro devices that appear in your telecommunication device, like your cell phone. By reducing the loss due to the echo, we can improve the performance of your cell phone, and especially the performance of the battery, the lifetime of the battery of your cell phone.
Other projects that we're working on are leadership program, which everybody in the center will have an opportunity to participate in, to really look at how we can be innovative in the way that we deliver content and materials in teaching, in mentoring, as well as in research opportunities for both undergraduate and graduate students. And part of this will also lead into a higher level leadership training opportunity for members of our community that want to go into administrative roles in their career sometime in the future.
When we visit each of the centers, we'd like to emphasize bringing together the work that goes on at the University of Arizona, where the center itself is located, and the work at the various universities.
In terms of sensing, we're looking at two types of applications. One is sensing the environment, the other one is sensing engineered structures. For the environment, we are using not acoustic waves, but their equivalents that exist in the ground, which are seismic waves. And we're using seismic wave and the geometry of seismic wave to monitor in a continuous manner the change in the permafrost in the Arctic. In terms of engineered structures, what we're doing is we're using also the geometry of acoustic wave to detect flaws or defects in these structures, like engines of airplanes or wings.
Another couple of exciting programs that we have, which are targeting undergraduates specifically, is our signature Research Experience and Mentoring program. Unlike a traditional REU, or Research Experience for Undergraduates, that take place in the summer only, and they're amazing, immersive 8-week programs, our program continues into the fall and spring semesters. So it's essentially a 12-month mentoring and research program. And in the fall, the students learn a lot more academic skill sets, such as submitting an abstract to a poster or a presentation that they will be making the following spring. They also learn a lot of other skills that help promote their research, their ideas, and themselves into both the workforce or their academic research pathways, should that be the path that they want to pursue. In addition to the REM program, we also have a community college workshop program, which is meant to tease and invite community college students to learn more about topological acoustics, so that as they consider transferring into one of our 9 institutions, they can actually choose a topological acoustic pathway. So the workshops will be the equivalent of about 25 to 30 hours of experiences being exposed to our labs in a hybrid manner, as well as having them investigate a little bit about the societal impacts of the work that could impact their communities.
With our members, we're developing intellectual property as well as guiding research and educational activities to enhance the convergence of the NewFoS Center's work. We work also with industry. With industry, we're looking at working together with industry for internships, for laboratory work with the center itself at the industry location, as well as jointly developed intellectual property and inventions, so that we can push out the information that's being developed in the research to quickly industrialize and capitalize on the technology that comes from the science developed by the centers. We also work very closely with public stakeholders and government officials to keep them abreast of the work that the center is doing in developing a workforce that will be able to work with topological acoustics and the advances that the center makes for the benefit of the entire society. Thank you.
We're also looking at possibility-driven projects or seed projects. And one of them, for instance, is focusing on the interaction between acoustic waves and biological waves. Biological waves like calcium waves, which are ubiquitous in your body and drive the physiology of your body. So overall, NewFoS is exploring a very diverse field of research. As I said, ranging from quantum information science to telecommunication to sensing to biology, and especially the use of topological acoustic waves and their extraordinary properties in advancing technologies in these areas.
I hinted at the textbook early on when I started this, so I want to kind of go back and revisit that and finish with that. The textbook is going to be the first signature textbook. You're going to hear about it from the researchers when they introduce the research side of things. But the textbook is going to be fully online, it will be open source, and it will be interactive. So we will have elements of the textbook that, one, takes a bite-sized approach to accessing concepts that are complex yet presented in a simple way. In addition to that, we will have links to other materials and resources that complement what the core of the chapters are. Furthermore, we will be involving undergraduate students in reviewing the chapters, but also some of the lessons that our researchers will design tied to the textbook, and the students will have the opportunity to provide feedback on the learning experience, how they might amplify it by adding additional learning activities that they think would be helpful to future students that are pursuing or interested in this field.